Today's tie, it's got Einstein on it. This was your classmate in the other section, Spencer Seiler. This is his tie, so you can thank you for this tie. Again, remembering dress number and the people that are victims of human trafficking. Doesn't really completely match the shirt. I was doing my best. There is some black in the shirt, no orange, but I guess it doesn't look too bad. All right, the first thing I want to do today is do a triple integral calculation in a couple different ways. These things are definitely tough to do, and so it takes work, and so that's why I was suggesting that you try practicing beyond what you had for your completion assignment. We'll do an example here today. So let's let W be the portion of the half cylinder defined by, first of all, this inequality, x squared plus y squared is less than or equal to 4, and this inequality, x is greater than or equal to 0. And also, between two graphs, you want to think of these as graphs of functions of x and y. The 0 function, which is a horizontal plane, and the function 3y, which only depends on y, that's going to be a plane sort of slanted in the y direction like that. If you were given this task to find the mass based on this density, as is, it's a pretty tough thing to do without help. It's tough to draw. I had a lot of trouble in the last class drawing this accurately. I'll try to do better in this class. So you've got your three-dimensional coordinate system. I typically draw the positive directions like you see here. It might be good to also lightly draw the negative directions for x, y, and z. Let me lightly draw in the xy plane here. That's probably a good thing to start with. And let me also draw in a circle of radius 2 centered at the origin in the xy plane, because I've got this inequality here. That's probably good to start with. So you have to draw with some perspective here. Something about like this. It's hard to get perfect. Probably impossible to get perfect. Something about like that. And then you want to imagine translating this up and down, theoretically forever and ever, to get the entire cylinder. To emphasize three-dimensional nature, or the fact that it's sitting inside three-dimensional space. It is a solid, I guess, because of that inequality. We also have the second inequality there, x is greater than or equal to 0, so in this picture that would be in front of the yz plane, in front of the board. Like we sketch the yz plane in about like this. I guess I've drawn it. You don't want to always think of it as the plane of the board, maybe coming out of the board slightly over here. Something about like that. You want to think about the part of the cylinder, the half cylinder, that's in front of that in your perspective here. So maybe draw a line like that. Try to imagine the half cylinder, although again, theoretically this goes on forever up and down. Then we cut this with, well, first of all, the xy plane, z equals 0. So now we consider what's above the xy plane, and also this plane, z equals 3y. Think of it as an equality there to draw the plane. That would be a plane that's slanted about like this. Either go through the x-axis, it's slanted. How can I draw it? Maybe about like this. Goes down to over here. And you're looking at values of z in front of the board and above the xy plane that are underneath that plane there. Something perhaps about like this. See that? It's tough. And if I gave you an exam question on the final just like this as is, this might be the toughest part of the problem, is trying to draw it accurately. So what could I do to make it easier on you, to give you some help? I might go ahead and put a picture of the solid in there with Mathematica, as I will show you now. That might be one way we can do it. Here it is, but again, remember Mathematica's orientation is to take the positive x-axis to the right and the positive y-axis into the screen, so we are not seeing the picture as I've drawn it. You would have to rotate it about like this to see it as I've drawn it. Let's make it more or less opaque. Let's see if we can do it opacity in here. Does that work? Plot style, opacity, 5, I think that'll work. To make it somewhat see-through. Something about like that is what I was trying to draw. And by the way, the edges along here look kind of rough. That's imperfections in the graph. It would be smooth in actuality. If I plot more points than 70, it'll probably look smoother. Hopefully. Takes longer, and you don't gain much smoothness. It should look smoother than that, though. Okay, so I did better on that than the last class. I think I'm going to tell them to watch the first 10 minutes of this class so you can see my drawing better. Even though I had colors with it, it was just I didn't start it right. That was the problem. So I figured out how to start it better. All right. So how do you now find the mass of this thing? Again, you integrate the density function over this solid, the density function here being z squared. Ultimately, the directions say to do it in cylindrical coordinates, but it's actually possible to do it in rectangular coordinates. It's not too hard. Initially, when I did it, I thought it might be kind of hard because there are some square roots involved, but the square roots end up going away. How can you do it in rectangular coordinates? You want to, first of all, imagine projecting this onto one of the planes, the xy plane, the yz plane, or the xz plane. Here it's fine, probably easiest to imagine projecting it down into the xy plane. Imagine there's a light source shining straight down. What is the shadow of this thing on the xy plane? It would be this set right here. That would be the projection of this set down into the xy plane, its shadow on the xy plane. Of course, if it was actually sitting on the xy plane like this, you wouldn't actually see the shadow, but theoretically there would be a shadow underneath it. When you write the triple integral of this density function over W, the book's main way to emphasize calculating this is to, in fact, think of this solid as a vertically simple region over the two-dimensional domain that you are projecting it down onto, meaning you think of the outer two integrals as kind of going together, and the inner integral is by itself. With respect to, in this case, since I'm projecting down into the xy plane, thinking of it as vertically simple, I want z to be the inner integral. So I do the inner integral with respect to z. The outer integral I'm representing as a double integral here initially over d, where d is this domain, this two-dimensional domain, the shadow down here, that's d. If you redraw it in a regular xy plane, d would look like this. It would be a quarter of a circle. The radius of the circle, because of the 4 there being the same as 2 squared, would be 2. That would be d, the domain of the outer double integral. Think of the inner integral with respect to z. Initially, we put a dA there for that outer double integral. But then once we've done the inner integral, we can either pick dx or dy, or dA, when we're not doing another coordinate system. What are the limits of integration for z? Anybody want to tell me? 0 to 3y, yeah, it's right there. Z goes from 0 to 3y. This region, this solid, is vertically simple. It's between the graphs of two functions of x and y, very simple functions. The 0 function is the z equals 0 is the xy plane, and the slanted plane, z equals 3y. And then you can do the outer two integrals, either thinking of this as vertically or horizontally simple. I usually sort of by default tend to think of it as vertically simple, which means x is going to be the outer integral. X goes from 0 to 2. For each x between 0 and 2, looking up here, y goes from 0 up to that point. Get that in terms of x, it's going to be the 0 to square root of 4 minus x squared. The function again is z squared. Here's how we do the integral in rectangular coordinates. I'll walk over here to actually do the integral. It's actually not too bad. Even though there's a square root of 4 minus x squared there, it turns out nicely. Do the inner integral with respect to z. Get a 1/3 z cubed. Z goes from 0 to 3y. And you've got your dy dx. Plug in 3y in place of z. You get 3 cubed is 27, divided by 3 is 9. You get a y cubed. Plug in z equals 0, you get 0. So that wasn't too bad. The inner integral. Now do the middle integral, which is now the inner integral of this double integral. Get 9/4 y to the 4th. Y goes from 0 to square root of 4 minus x squared. And luckily, because that's an even power, that's what's going to make it easier to do. If that were an odd power, then we'd be in trouble as far as difficulty level. The square root of 4 minus x squared to the 4th power is going to be the same as 4 minus x squared quantity squared. Plug in 0, you get 0. Bring the 9/4 out. So 4 minus x squared quantity squared is what goes there. I've got to FOIL that. I get 16 minus 8x squared plus x to the 4th. One more integral to do. 16x minus 8/3 x cubed plus 1/5 x to the 5th. X goes from 0 to 2. Plug in 2, then plug in 0, get 0. When you plug in 2, you'll get 9/4 times 32 minus 2 cubed is 8. 8 times 8 is 64. 2 to the 5th is 32. Get a common denominator inside here of 15. So we get 9/4 times, see 32 times 15 is going to be 480. Here we have to multiply the 64 by 5 so that we get a 15 on the bottom. Multiply the top and bottom by 5. 64 times 5 will be 320. Subtracting that. Here I have to multiply both the top and the bottom by 3. 32 times 3 is 96. $40 minus 320 is 160, plus 96 is 256. Then we get some cancellation. A 4 goes away, leaving a 64 there. 9 and 15 cancel to give you a 3/5. So 3 times 64 is 192. 192 over 5 is the answer. And I guess that's going to be 38.4, I think. Yeah, 38.4. That would be the mass in whatever unit that you use. Let's confirm it with Mathematica. And let's also in Mathematica do it in cylindrical coordinates. Confirm it that way too. So go down here, do the integral. First I'll just type the integral into here, or use the palette here to get the integral in as is in rectangular coordinates. Just confirm that I did that full calculation correctly. 0 to 2, 0 to square root of 4 minus x squared, 0 to 3y, z squared, dz, dy, dx, 192 over 5, yep. Now let's do it in cylindrical coordinates. R, theta, and z, right? Don't forget the extra factor of r that you can calculate actually from a Jacobian determinant of a 3 by 3 Jacobian matrix, actually. We'll take the time to do that. That's dv in cylindrical coordinates, r, dr, d theta, dz. Or maybe I should put the dz on the inside. Make it dz, dr, d theta. Let's do it that way. That's probably easier to do. Theta is going to go, look at the picture here. Theta is going to go from 0 to 90 degrees, 0 to pi over 2. We're in the first quadrant there above the xy plane. So theta goes from 0 to pi over 2. I haven't plugged my function in here, by the way, yet. We're going to do that too. What about r? Somebody tell me what r does. 0 to 2. R is the distance, the horizontal distance between the points and the z-axis. If you project the points down the xy plane, it's the distance to the origin. In three-dimensional space, it's the horizontal distance between a given point and the z-axis. And that goes from 0 to 2. The disk had radius 2. For each r from 0 to 2 and theta from 0 to pi over 2, what does z do? This is the trickiest part. 0 to what? What should I put up there? Yeah, exactly. Z went from 0 to 3y, so in terms of r and theta, z goes from 0 to 3r sine theta, since r sine theta is equal to y. Don't forget the density function itself, z squared. It's the same answer. Would this one be easier to do by hand? Think a little bit, at least if you know how to integrate sine cubed. First integrate with respect to z, you'll get a z cubed over 3. Plug in 0 and 3r sine theta, you'll get an r cubed, and ultimately an r to the 4th, and a sine cubed theta. Integrating sine cubed is finally ultimately what you'd have to do at the very end, the very outer integral. Let's think about an antiderivative of sine cubed. I did talk about this the other day, actually. But let me be a little bit more specific. Think of sine cubed as sine squared theta sine theta. Replace sine squared theta with 1 minus cos squared theta. Then do a substitution. You can let w or u equal cos theta. In this case now, dw would be negative sine theta d theta. You'd end up with integral, switch around these things because of the negative sign, w squared minus 1 dw. That'll be w cubed over 3 minus w plus c. Then replace w with cos theta. You get 1/3 cos cubed theta minus cos theta plus c. So if you know how to do that, it's fairly quick. You can even skip the w step if you are good enough at thinking about simple substitutions like that. And that would be the last outer integral that you have to do. That would be the hardest step. Any questions? Did I write something funny?
No, there's a simple substitution.
Oh, okay. Yeah, simple substitution compared to these two-dimensional changes of variables, I guess. All right, and we could do things like find the center of mass and stuff too. I think I will do that before I put this on Moodle. I'll have Mathematica find the center of mass, and I'll probably graph it in there too. The centroid. Well, the center of mass, because the density is not constant. I might also graph the centroid if the density were constant. They won't be in the same spot. All right, for the rest of the class today, though, we need to talk about line integrals. I know I introduced vector fields. That was the main thing we did on Wednesday at the end. And I am going to talk about vector fields today still, but first I want to talk about what are called scalar line integrals. First thing I should mention that is this name line integral actually is not ideal. We're not integrating over lines, we're actually integrating over curves in general, although the curves could be lines. So it would be better to call them curve integrals, but line integral is the standard terminology. So we'll stick with that. What are scalar line integrals about? Well, as an example of an application, yet another mass application, you can use them to find the mass of a thin wire, for example, in the plane or in three-dimensional space. Let's think about that intuitively, as we typically do. I think perhaps next Monday, I might try to spend some time talking about a little bit more rigorous perspective on this stuff. Mathematically speaking, thinking about limits a little bit. Not in a ton of detail, but just to warn you about some things. You know, we take the easy route and assume everything's nice for the most part, but definitely things can go wrong. You can encounter strange enough wild functions as we did, what was that, about a month ago? Where things are weirder than you might imagine. Those things are supposed to be warnings that if you are going to become a mathematician, for example, you would want to worry about such things. Mathematicians are trained to be concerned about possibilities like that. But we take the intuitive perspective, partially because it's quicker, and maybe more fun, and maybe more helpful for physics, chemistry, engineering classes. So let's imagine a thin wire now that does not have a constant density. And we're going to imagine that we placed an XY plane in here. We've imposed a coordinate system, a rectangular coordinate system. And this wire is sitting inside this plane, maybe on the table. And the density is not constant. Let's pretend it's some function of x and y. The rho of xy would be the linear density here, say, in grams per centimeter, grams per unit length, because it's a thin wire. It's effectively, from a modeling perspective, a one-dimensional object. You ignore any thickness to it. So this would be a linear density, but it's a function of the position along the wire. Would it have a nice formula? Probably not for real wires. It would probably be no formula that you could figure out very nicely, at least to get it exactly right. However, as an idea, it's still there. There is some function, some abstract function that you probably can't find a formula for that would represent the density of this wire as a function of the position. What's the total mass? Well, you imagine getting your scissors out, your wire clippers, and cutting this wire anywhere you want into tiny little chunks, okay? Tiny little infinitesimally small chunks, smaller than an atom, smaller than an electron. You say, how's that possible? Is an electron a point particle? I don't know. Maybe you can get smaller than an electron. It's so small, effectively, we treat it as a point. Anyway, we imagine zooming in so close there that it's a little tiny piece of a certain length. Let's call that length ds. Why ds? That was what we used way back in chapter 13, I think. S represented arc length, which we always call distance traveled. S is the standard unit letter to use for arc length. I don't know why. ds then represents a tiny little infinitesimally small chunk of arc length. If we multiply that length in centimeters times rho in grams per centimeter, so we're going to get the tiny little mass in this tiny little chunk. This ds is supposed to represent that piece of that curve right there. You might say dm is rho of xy ds. Grams per centimeter, centimeters giving you a tiny chunk of mass in grams. Then to find the mass, here's the fun part. Right? You should feel almost like an urge when you see things like that. Must integrate. Oh, that feels good. Right? The total mass is found by adding up the little masses. You imagine the integrals in addition. Okay? What should we put down there? D? No, there's no domain here. That's not a two-dimensional domain, at least. There is a curve. Maybe I should call the curve C. And so since we've gotten on this cursive kick, let's make it cursive C for the curve there. We're integrating over the curve. Can you see that down there? Showing up. I should probably put it up here. So total mass is the integral of the dm's, adding up the dm's, so to speak, over the curve. But that begs the question. Oops. Okay. Not a mistake. I need to replace the dm with rho of xy ds. But that begs the question, how do you calculate that? What you do is you parameterize the curve. Parametric equations never go away in this class. Right? They're always there somewhere in the background, useful in some way. We want to parameterize the curve. Parameterize the curve. In this context, it turns out it doesn't matter what direction you parameterize it in, the motion is what I mean. With the vector line integral, the next section will matter what direction. If you look at that first line, it says vector fields along oriented curves, the direction will matter there. But here it doesn't matter. We can do it left to right or right to left. Find some function c of t. You could call it r of t if you like. The book tends to call it c of t here in this chapter, I guess to match the c there. For t going, say, between a and b. More intuitive calculations. What is this ds? What's another way to think of it? Another way to think of it, informally speaking, hand waving, is ds dt dt. Pretending like you cancel the dt's to check it. There's no pure mathematicians walking by the door looking inside suspiciously. Actually, I'm a pure mathematician. What am I talking about? But not for this class. We're being informal. Well, what's ds dt? Give me a word for that. One word, 5 letters. Starts with an S. Speed. S is arc length, distance traveled. ds dt is its derivative, speed. I could write speed dt. I could also write this. What do you think I should put in there? C prime of t, yeah. It's the length of the velocity vector is the speed. And that tells you what you ultimately do. You replace ds with this. You need to plug c of t into rho as well, because you need to keep track of the density as you move along the curve. And you integrate the resulting function from a to b. So this is calculated by doing the integral from a to b of rho of c of t. C of t is going to give you a point as t changes, x, y, times the length of the velocity vector, in other words, the speed, dt. So here I have an example. Let's also make a plot of this. Contour plot of rho. Contours, let's do a lot of contours. Let's do 100 contours. I'm going to let, with the parametric curve there, t comma t squared, that's a parameterization of the parabola y equals x squared. You can parameterize that parabola with t comma t squared. Essentially, you're letting x equal t, and therefore y equals t squared. Graph it with parametric plot. C of t. T goes from 0 to 2, say. There we have it. You might be wondering, well, that density function is defined over the whole plane. What do you mean it's, what about the wire? You don't worry about the fact that the density function is defined over the whole plane. You only focus on its values on the wire. Okay. The values, rho of 0, 0, look at the formula up here, is 4. That's the minimum density, 4 grams per centimeter. And then rho goes up in value here. It looks like our contour interval is 0.75. Going from 4 up to around 20 or so. What's the average density? Halfway between 4 and 20, that would be 12, but sort of more length in this wire is in the lower regions, the darker ones, than the higher ones, so probably the average density is less than 12. And in fact, I guessed ultimately in the last class, ultimately it's a little bit above 10. I forgot what exactly, maybe 10.5 or something. If you take 10.5 and you multiply it times the length of this, that should give you a good estimate for the mass. How long is that though? Actually, to find the length of this, I'd have to do another integral, an arc length integral. Integrate the speed itself to find the length, but let me just see if I can eyeball it here. The length of the straight line between those 2 points is, that's points 2, 4, be the length of the vector 2, 4, square root of 20, between 4 and 5. This curve is, of course, longer than that. I don't know, 5? Just guess 5. Actually, I didn't do this in the last class. I found the exact answer, or a more exact answer. I'm going to make a rough guess of 52.5 grams for the mass of this wire. Let's get mathematically to do this more precisely. I'm going to turn the light back on so I can see my keyboard. Let's see. The function we're integrating. Let's look at the speed function here. For fun here, we do square root of, remember this, c prime dot with itself. That'll be the speed. That's the function we can integrate to find the length. T goes from 0 to 2. Integrate that function to find the length. Oh, yikes. Hyperbolic arc sine. What in the world? You probably never dealt with hyperbolic arc sine before. Hyperbolic arc sine, just like hyperbolic sines and cosines are essentially exponential functions, hyperbolic arc sines and arc cosines are actually related to logarithms. But anyway, that's about a length of 4.65, so I should have used a 4.65 down here. I should have guessed better. 4.65. So I'm guessing a mass of 48, 49 grams or so. We need to multiply this thing by rho of C of t. figure out the function we integrate to find the mass. Doing that by hand is not even possible. Let's see if we can calculate an antiderivative of this. Evidently it is possible, but it again involves a hyperbolic arcsine. How about a definite integral from 0 to 2? It's that, which is about, drum roll, 47, 48, 49. Hey, 49. Okay? So there's a more precise estimate for the mass. Now you might be thinking about the practicalities of this. Why would you ever find a function rho and do this integral to find the mass of a thin wire? Why don't you just weigh it in some gravitational field? Deal with the gravitation, the acceleration due to gravity. Well, of course you wouldn't do it this way, but as an idea, it's certainly right. I suppose some people have debated it, but this theoretically should give you the right answer if somehow you could find a formula. In an abstract sense, even without a formula, it represents the mass. Could it possibly have any practical applications? Well, the one I mentioned in the last class, I'm not sure how phony this is. Just imagine that's a road through some city or something, and we're looking at it on a map, and we're way back. Maybe this is a scale of maybe this is 30 miles along here. And rho is the density of cars, say cars per mile. Now cars are discrete things, so a continuous density like that would be just an approximation. But if you could integrate the density of cars per mile over this curve, you get the total number of cars on the road. That's going to change over time. Cars are moving. So the density ultimately would have to depend on time as well. And you have to do a bunch of integrals for different times to continually update how many cars are on the road. I can imagine that more in terms of a simulation, a computer simulation, more than actually somebody going out there and seeing how many cars are out there and what the density is to calculate the total number of cars. If you use that in some sort of simulation, that's where I could see it being useful. But I've never done such a thing myself, it's just in my imagination. All right, so that's a scalar line integral. What about a vector line integral? Again, first of all, the curve itself now must be oriented, whereas with the scalar line integral, the curve is not oriented. Meaning, as a practical matter in terms of your homework problems, that you either have a drawing with arrows along your curve. In this case, the orientation would be from left to right. It could have been the other way, right to left. Or the orientation is described verbally as left to right, right to left, or maybe if you're going around a closed curve, counterclockwise or clockwise. So there's either a picture or a description of what the orientation is. And the key thing is when you actually calculate the integral, you have to parameterize with respect to that orientation. If the orientation in this picture is right to left, you should not pick a C of t that goes left to right. That would give you the opposite of the right answer, which is good to know anyway. But you want to make sure you orient the motion of C of t, motion that it models, in the appropriate specified direction of the orientation that's given. Calculating vector line integrals actually ends up being easier than calculating scalar line integrals. However, understanding the meaning of vector line integrals is harder. Three applications are hinted at here. The first application being to find the work done by a force. The second application being to, in some way, fluid mechanics application, measure the circulation of a fluid around some closed oriented curve, whatever that might mean. We're not actually going to be very precise about that in terms of what it means for fluid mechanics. The third application, you can be a little bit more precise about what it means for fluid mechanics. You can measure something called the flux, the amount of fluid past a membrane, flowing past some permeable membrane per unit of time. It's called the flux. For a two-dimensional example, it would be a two-dimensional fluid flow. It would be like in cubic centimeters per second or something, or excuse me, square centimeters per second. In 3 dimensions, if you're in 3-dimensional space and you're flowing through some 2-dimensional membrane, then the units would be, say, in cubic centimeters per second, or in liters per second, or in gallons per minute. Those would be the kinds of units you use for a flux. Actually, this third one is a different type of line integral than the first two. I'll have to talk about what that means next Monday, but these are the 3 main applications. So again, you orient your curve. So I'm drawing just a general curve here. And now what you have to imagine is this is embedded inside a graph of a vector field. So in the background, you've got a bunch of arrows that can be doing lots of different things. Getting shorter, getting longer. That's supposed to represent the graph of some vector field, capital F of x comma y. And you are thinking of this initially as integrating the vector field over this oriented curve. Here's the notation. Integral sign. You put your c down here. And most of the time you don't bother somehow emphasizing that it's oriented with some special notation. There are some special situations when c is a closed curve where you emphasize a counterclockwise or clockwise orientation by putting a little circle there with an arrow in an appropriate direction. But here we just need to understand that c is an oriented curve. You put your vector field right there. Let's not bother with the inputs there, just write a capital F. It is important, I think, to practice making some things vectors and some things not vectors, especially right with what I'm about to do now. You dot this, dot product with ds, but this ds is not a little tiny arc length. It's a little tiny infinitesimally small vector. You would think you'd do this, but it's actually more traditional to do this. And in the book, just the S is bold-faced. It'd be better, actually, probably, if the whole thing was bold-faced. But that's how you write it. What is this going to represent? Okay, what do we want it to represent? Let's think about the first application. Ultimately, we want it to represent the work done by the force field. Okay, so this is in some force field. This is like a gravitational field. Well, of course, gravitational fields don't typically look like that. Some sort of force field. It could be an electric field. Maybe there's some charges around creating an electric field here. And what do you want this integral to represent? You want it to represent the work done by the force. Okay, now, plenty of you are in physics or have had physics, and so you know about the work done by a force, but some of you have not had much physics, even though this is maybe the closest to physics that you've had in this class. And so what is the work done by a force? In a simple situation where you're like pushing this table horizontally with, say, a horizontal force, the work that I did on the table is the magnitude of the force, assuming I did a constant force, times the change in position, the distance traveled, really. That would have units of newtons times meters in standard units, and that converts to what's called joules, which is a measure of energy. So effectively, in measuring the work that I do on this table, in moving it that far, I have essentially described the amount of energy that I had to expend. It's not exactly right because there's not a table involved, there's my body, and there's the floor, and that kind of stuff. But basically, I think that describes the amount of energy that I put into making that table move. If you apply the force not parallel to the motion, but say downward here, then you take the component of the force in the horizontal direction. You have to essentially do a projection kind of thing, thus the dot product there, and multiply that times the distance traveled. If the force is not constant, if you're going to calculate the work done, you have to do an integral. Now this integral would be over a straight line, but you'd have to do the integral if the force is not constant as I push it. What does work mean, though? I mean, you know, it's evidently related to energy. You can say that the net work done on an object ultimately is equal to its change in kinetic energy, which is related to how fast it's going. So if I speed this up, the net work done on it is positive because the change in kinetic energy is positive. I'm doing work on the table, but also the floor is doing work on the table in the opposite direction, the friction. But I did speed it up, so evidently the change in kinetic energy is positive, and the total work done, the net work is positive. So there's these forces going on. I think next week we'll apply this to a gravitational field, thinking about the planets going around the sun. And we'll think about it in terms of what's the work done by the gravitational field on planets. Since the planets in Kepler's laws come back to where they started, ultimately, over the course of an entire orbit, the net work done is zero as it comes back to where it started. Anyway, give me a couple minutes here. How do you actually calculate this now? Well, I'll just tell you the answer, and then on Monday we'll talk about intuitively why it works and what it means. You parameterize C, just like before. You plug the parameterization into the vector field. You dot this with the velocity vector, and that's the thing that gets integrated from A to B. And this is actually an easier integral to do than the scalar line integral in general, because in general with the scalar line integral, you've got a square root involved, typically, unless it somehow simplifies nicely. With that, unless the formula for f or c itself has a square root, and in most of our typical examples they don't, that's going to be a pretty easy integral to do typically. So doing it, once you've got your parameterization, is very easy. Understanding what it means, that's the hard part. Okay, and that's the main thing I want to focus on, is understanding what it means. Understanding what it tells you about f, especially. It'll also tell us whether f is a conservative vector field or not, whether there's a potential function or not, we will see. Okay? Have a great weekend.